In this next video, we're looking at moment of inertia, and this talks about why something is easy or hard to rotate. So what we talked about before, we said mass is inertia is a property of mass, right? The resistance of something to move is because of its mass. So just like when we had mass resisting linear acceleration, we have moment of inertia to resist rotation or angular dynamics. So let's take a moment and look at this. So net force equals mass times acceleration. So this is just the fact that inertia, the more mass you have, the more you're going to resist moving, meaning the more force is required to get you to accelerate a certain amount. Now, we know that A equals R alpha. So net force is equal to M R alpha. Now I'm going to multiply both sides by R for a reason that'll become clear in a minute. So we're going to R equals F equals R M R alpha, which in other words is just M R squared times alpha. And then I can move that R inside the sum, basically multiply each force times R. And if you notice, this RF is just torque. So in other words, I have net torque is equal to mr squared alpha. And so we have something that looks very similar to F equals ma, but it's got torque and it's got alpha, and then it's got this funky thing here that's functionally like the mass from before. So we call this moment of inertia I, and that's equal to r squared, or technically it's the sum of all the tiny masses times r squared. This I is the moment of inertia. And it's just a way to measure how much something is going to be hard to spin or to not. And so if you look at this, you can kind of sense if something has more mass, it's obviously going to be harder to spin. If that mass is farther away from where you're trying to spin it, it's going to be harder to spin as well. So this is the classic example of if you've got, an ice skater and they're doing a spin and they've got their arms out, right? The mass is kind of spread out, but then if they bring their arms in, then all of their mass is kind of really close to this axis of rotation, so their moment of inertia goes down and they'll spin faster. It's easier to spin something where all the stuff is kind of close together. You can test this for yourself. If you go and get like a little stick and then put a weight at the end, if you've got like a set of weights, and if you try to spin that around while holding the end here, it's pretty hard to get it moving. Like you have to push really hard and it strains you. But if you hold that same stick with the mass on it and you try to rotate it like so, it becomes a lot easier. And that's because it's got a lower moment of inertia when it's angled like that. And so how do we calculate the moment of inertia? Well, if you've got a bunch of stuff, calculate all the individual moments and add them together. So let's look at an example. I'm going to take a shape that's going to be just some thin wire with a bunch of beads attached to it. So this one has a mass of m, this one has a mass of 2m, this one has a mass of 3m, and these are all, we're going to say, wires with length of r, and I'm rotating it around this point. So the moment of inertia is going to be the sum of all the individual m times r squareds. Let's call this d so we don't get confused. So this will equal the first m, this one up here, times the distance from the pivot, which is d. Then I'm going to do this bottom right one, which is going to be 3m times, again, distance d. Then I'm going to do the top right, which is 2m. This distance right here is square root 2d. So this will be times square root 2d. And it should be r squared, so these need to be squared. And we get md squared plus 3md squared plus, that's going to be 4md squared. So the moment of inertia ends up being, in this case, 8md squared. This is something that once you get some practice with it, it'll make more sense, but the kind of crux that I want you to take away right now is the farther the mass is from the pivot point, the harder it is to make that thing rotate. So that's where we lead into a bunch of examples like this. You don't need to memorize any of these. I believe on the AP test, they will always give them to you, but we can kind of look at some and compare them. So let's look at, for example, a solid sphere and then a thin spherical shell. If we look at this, a solid sphere means the mass is distributed kind of throughout the whole object, right? So there's some mass here, some here, some here, some here, some here. For a spherical shell, it's just on the outside. Same shape, same mass, same radius, but because this has some of the mass in closer to this rotation point, you'll notice that the moment of inertia is smaller. These are all calculated using calculus. You don't need to worry about it for this class, but I just wanted to point that out. Same thing with these two rods. If my axis of rotation is in the middle, I only get ultimately half L away. Like the mass can only get half L away from the center. Whereas if I'm at one end, the mass can get a full L away, and therefore we see that the moment of inertia is less for the one that can only get half an L away. This is something that we'll talk a lot about in class for practice, but we're just giving an overview for now. If you have any questions, let me know, and I'll be happy to go over it with you again in class.